Let C be the set of all integers n such that n is equal to 6r minus 5 for some integer r, and let D equal all of the integers m such that m equals 3s plus 1 for some integer s. Prove or disprove each of the following statements. Part A, C is a subset of D. So we have to ask ourselves, is everything that's an element of C also an element of D? I think it would be helpful in this problem to write out the elements of C. So these are all the integers that are of the form 6r minus 5 for some integer r. So we can think about some values of r that we can plug in here to get some integers. So if r is equal to 0, we can get negative 5. If r equals 1, we can get 1. If r is 2, we can get 7, and then 13, and so on in both the positive and the negative direction here. Now I'm going to plug in some values for s as well, but I'm actually going to start at s equals negative 2. If you plug in s equals negative 2, we also get negative 5. And then if we plug in s equals negative 1, we get negative 2. If we plug in s equals 0, we get 1. S equals 1 corresponds to 4. S equals 2 corresponds to 7. S equals 3 corresponds to 10. S equals 4 corresponds to 13, and so on. I'm writing all of these numbers out to show very clearly that the elements of C are also elements of D. This makes it much easier to prove and disprove the statement. Let's actually do part B first. The reason why part B is easy to start with is because D is not a subset of C. We can find an element in D that's not in C. For example, the number 4. 4 is an element of D, and 4 is not an element of C, which immediately means that D is not a subset of C. So that's part B. Let's do part A, because A is true, which means we have to prove that. How do we prove that C is a subset of D? Well, what we can do is we can take an arbitrary element from C, and we can ask ourselves that even though the object is arbitrary, do we have enough information about this arbitrary element to show that it's also in D? So what we're going to do is we're going to let lowercase c be an element of capital C. Now, by definition, that means that there's some integer such that c equals 6 times that integer minus 5. So I'll say c equals 6k minus 5 for some integer k. Now we want to show that c is also an element of D. But to do that, we need to pass this test here. We need to show that c can be rewritten as 3 times an integer plus 1. So we need to change this expression here, 6k minus 5, into 3 times some integer plus 1. Now the trick here is that here we have a minus 5. But we don't want a minus 5, we want a plus 1 here. So what I'm going to do is I'm going to rewrite this as c equals 6k minus 6 plus 1. By rewriting the minus 5 to be a minus 6 plus 1, now we have this plus 1, which is a necessary part to show that this element is in D. The next thing we have to do is factor out a 3 from everything else. But luckily for us, the other element here is minus 6, so conveniently we can easily factor out a 3. So this is 3 times 2k minus 2 plus 1. Now 2k minus 2 is an integer, which means c equals 3 times l plus 1 for some integer l. Now I could have used the letter s since s is a local variable to this definition of D, but just to keep things a little bit more coherent, the important fact here is that 2k minus 2 is just some integer, since integers are closed under multiplication and subtraction. And so c can be rewritten in the exact format that it needs to be rewritten as in order to show that c is an element of D. So this means that c is an element of D. I should emphasize that these are all lowercase c's. So we started with an arbitrary element from capital C. And even though we don't know what this element lowercase c is, we know some information about the equations that lowercase c must satisfy. And we can use that information to show that therefore C is an element of D. Since C was arbitrary, then this means that this is true for all elements of C. We can replace lowercase c with any element of capital C, and this proof would show that that element is also an element of D. So therefore, C is a subset of D. Thanks everyone, and I'll see you in the next video.